So now there's a special property that we need to use in order to simplify radicals because not every radical will disappear and become a nice, pretty polynomial term, okay? So in order to simplify radicals, we're going to use this property, which says the nth root of a times b is equal to the nth root of a times the nth root of b. Basically, if I have multiplication in the radicand, I can split it into two separate radicals being multiplied together, all right? So let's take a look at how this works. You did this when you were simplifying square roots with the Pythagorean theorem in geometry. So we're going to bring that back, but we're going to extend it to higher order roots instead of just square roots. All right, so when I look at the number 147, now it doesn't really look like there's much of anything that goes into it, but this is a square root, so I want to know, is there a perfect square that goes into 147? Well, 1 is never going to help us. 4 doesn't go into 147. 9 does not. And so on and so forth. But if I look, eventually I will find 147 is actually 49 times 3. Okay? So I can split this apart into the square root of 49 times the square root of 3. Well, the square root of 49 is 7, and then I have the square root of 3 left. So this is the reduced form of the square root of 147. So the first number here, the 49, is a perfect square, something I can actually square root. And the second number over here is something that I cannot square root. I want to go with the biggest perfect square possible so that I only have to reduce one time. Okay? All right, let's take a look at problem B. Now I'm looking at a cube root. So I want to know, well, what perfect cube goes into 72, not what perfect square. So when I look at my list of perfect cubes, I've got a 1, which doesn't help anything. Then I've got an 8. Well, this is 8 times 9. Okay. So I can break this apart into the cube root of 8 times the cube root of 9, which comes out the cube root of 8 is 2. And then I'm left with the cube root of 9. And the cube root of 9 cannot simplify because the perfect cubes are 1, 8, and then 27. And none of those go into 9. So this is my final answer for part B. Let's take a look at part C. Now I've got a perfect power of 5 here. Okay, I've got the fifth root. So I need to break this apart into the fifth root of, in this case, it'll be 32 times 2. And I can do the fifth root of 32. I'm looking at that list of perfect powers of 5 to figure out what number to use. And the fifth root of 2. The fifth root of 32, is a 2. And then I have the fifth root of 2 left over, okay? So I'm referring back to that list of the perfect powers of 3, perfect powers of 4, perfect powers of 5, the perfect squares to figure out what factors to use here, okay? All right, so in addition to simplifying numeric expressions, we also need to simplify variable expressions, all right? So let's take a look at some of those. Now we're going to go through 6 of these, all right? What I'm going to do is I'm going to split this apart into part of it's a perfect square, the other part is not. So when I look at 150, well, that's definitely got 25 that goes into it. This is 25 times 6. Then I've got a to the 4th, b to the 6th. Okay. Now, a to the 4th is a perfect square because the exponent can be divided by 2. B to the 6th is also a perfect square because its exponent can be divided by 2. So when I split this up, I'm going to move the 25, the A4, and the B6 all together. I'm going to leave the square root of 6 by itself. Okay. I can actually square root this expression here. And then over here, the square root of 6 I can't touch. Okay. Square root of 25 is 5. Square root of a to the 4th is a squared. Square root of b to the 6th is b cubed. And then I've got a square root of 6. Now, any variable expression you need to ask yourself, do I need absolute value? So step 1 is decide, was this an even index root? Yes, it was a square root, so that means I might need absolute value. Second, did I have any odd exponents? Right here, this b cubed has an odd exponent. So I need absolute value around the b cubed to get to my final answer. So this is my final answer for simplifying part A. All right, let's take a look at part B. Part B is a cube root, so I want to break this into a perfect cube. Well, the perfect cubes are 1, 8, 27, and this 135 happens to be 27 times 5. Okay, you'll have a calculator to help you figure out what numbers go into these bigger values. Okay, so don't panic about that part of it. Now I've got k to the 13th. So I've got to break that up into a perfect cube and a non-perfect cube. All right, so what I'm going to do is I'm going to break this up. And I want to have the biggest exponent possible here so that I can actually divide that exponent by 3. So I'm going to go k12 and k to the first. And that's because the 12 plus 1 gives me the 13, but the 12 can be divided by 3, so I can eventually find its cube root. Okay. So now I'm going to split. Oh, sorry, I forgot to write the index here. Don't lose track of that index. I'm good at losing track of my index sometimes, so word to the wise, write the index first. All right, I've got a 27 and k12. Those are both perfect cubes. And then I've got a 5 and a k to the first. Okay, which I don't really need to write that one there, so I'm going to get rid of it. The cube root of 27 is a 3. The cube root of k12 is k to the 4th. And then I still have the cube root of 5k, which can't be simplified. All right, so now the question is absolute value. Well, it was a cube root, which is an odd index, so there's no concern here for absolute value. Only an even index root will have absolute value factored into it. All right, C. Perfect power of 4 because it's a 4th root. So, perfect powers of 4, let's see. We've got 1, 16, and then 81. 16 will go into 64. So this is 16 times 4. All right, x to the 9 I'm going to break up into x to the 8th and x to the 1st. And then the z to the 8th I can just leave alone. All right, so when it comes to the exponents, I'm trying to think about, oh, I did it again. Forgot to write my index. Sorry about that. I want to keep track of the exponent and the index in relation to each other, and I want to make sure the exponents inside are divisible by the exponent, the index out front. Sorry, I'm tripping over my words tonight. All right. We're going to make this now the 4th root of the 16 is a perfect power of 4, the x to the 8th, and the z to the 8th. Those are all perfect powers of 4. The non-perfect powers of 4 are the 4 and the x to the 1st. The 4th root of 16 is 2. The 4th root of x to the 8th is x squared. The 4th root of z to the 8th is z squared. And then we're still going to have the 4th root of 4x. Now, this was an even index problem, so I need to consider absolute value. But when I look at the things I wrote outside the radical, they have even exponents, so I don't need to actually worry about absolute value there. Okay, so this is my final answer. All right, what I want you to do is I want you to pause the video and try to do the next 3 problems. So we've got D, E, and F. I want you to pause and see if you can figure them out on your own. Okay, now that you've tried them, let's take a look at them together. So I want to simplify the 5th root of 16n to the 8th. Well, the perfect powers of 5 are 1 and then 32. So I'm not going to be able to simplify the 5th root of 16 at all, but I can deal with the n. So I've got 16 stays. I can make this n to the 5th and n to the 3rd. And now when I break it up, there's my index, sorry. I'm going to write the 5th root of n to the 5th first, because that's the one I can take the 5th root of. And then the 5th root of 16n cubed, I can't simplify. Well, the 5th root of n to the 5th will just be n. And then I'll be left with the 5th root of 16n cubed. This was an odd index problem, so absolute value is not a factor. Only even index problems will have absolute value involved. All right, let's take a look at E. E is back to square root, so I want to know what perfect square goes into 128. Now, there are lots of perfect squares that go into 128. I'm going to go with the biggest one possible, which happens to be 64. This is 64 times 2. All right, and then I've got the c to the 10th. Keep in mind, again, there's a 2 here. So this is going to be the square root of 64 and c to the 10th times the square root of 2. The square root of 64 is 8. The square root of c to the 10th is c to the 5th and then I still have the square root of 2. All right. Now this was an even index problem. I have an odd exponent here, so I'm going to need absolute value in the mix around the c to the 5th. So this is my final answer for problem E. And last but not least, F. All right, cube root. So I want to figure out what perfect cube goes into this expression. Now, 125 is a perfect cube. I'm going to split up the M15. Actually, I don't need to split up the M15 because this is a cube root problem, and I can do m to the 5th to the 3rd to get to M15. The K7 I'm going to split into K6 times K to the 1st. And then I'm going to break this apart. Cube root of 125, the m to the 15th, and the k to the 6th all stay together, times the cube root of just plain old k to the 1st. Cube root of 125 is 5. Cube root of m to the 15th is m to the 5th. Cube root of k to the 6th is k squared. And then I have the cube root of k left over. And because this is a cube root problem, not an even index, I don't need to think about absolute value. All right. So as you can see, there's a lot to think about here. It's going to take a lot of practice. So do your best with it and let me know what questions you have.